Good day, everyone. My name is Veronica S. Prudente, and I am currently the Training Director of Mathenic Philippines, a math enhancement program designed and created by Mr. Virgilio Y. Prudente Sr. We developed Mathenic because it is our advocacy to help in nation building by enhancing the mental aptitude, competence, and intelligence level of the Filipino students. We in this company are all recipients of government scholarships and subsidies, having been educated in the Philippine Science High School and the University of the Philippines, and we believe in giving back to the country that has supported us. We at Mathenic Philippines, together with our business partners in all the three major islands of the Philippines, Luzon, Visayas, and Mindanao, have been teaching children and adults Vedic mathematics-based modules or Mathenic since 2011. To extend the reach of Mathenic and Vedic mathematics tenfold, Mr. Virgilio Y. Prudente Sr., or Sir Ike as he is fondly called, wrote two books in maths, the 25 Math Shortcuts and the Algebra Made Easy as Arithmetic. 6,000 copies of 25 Math Shortcuts sold in less than 2 years. Mr. Kenneth R. Williams, founder of Vedic Maths Academy UK, wrote, "I like your book, Ike. It's packed with useful calculation methods, neat maths tricks, and amusing anecdotes, and all explained in a fun and very readable style. Good luck with it and all your other excellent endeavors." Mr. Rex Aurelius C. Rubiales, Dean of Mapua Institute of Technology's School of Industrial Engineering and Engineering Management, wrote, "The 25 Math Shortcuts is a great collection of mathematical shortcuts that everyone should know. With this book, the author tries to make math an easy subject to understand. And it's not often you see a math book written for all ages, a must-have for everyone." In the foreword of Algebra Made Easy as Arithmetic, Mr. Kenneth R. Williams wrote, "This excellent book from Virgilio I. Prudente is a welcome and much needed addition to the Vedic maths literature, and will undoubtedly be a great help to all those who wish to expand and enrich their knowledge of mathematics." Giovanni Tapang, PhD, Professor of Physics at the National Institute of Physics, University of the Philippines, Diliman, thinks that Mathenic mixed with practice would make anyone fall in love with algebra again, as it makes algebra as easy as arithmetic. Ms. Germary Atibagas, outbound educator, industrial and organizational psychologist, Managing Director for Lakbay Kalikasan World of Outbound Corporation, wrote, "Even right-brainers can easily understand the relationship of numbers and the logic behind the equations. This will be very helpful for visual learners to enjoy and even love algebra." Annette Lagman, PhD, a University of the Philippines Systems IT consultant and former math and computer science professor at James Madison University and at Affet University, wrote, "Algebra Made Easy as Arithmetic is a terrific book that offers something for everyone. Math lovers will be challenged to understand why the tips and techniques actually work. On the other hand, students who need some help with math can try out all the techniques and pick out the ones that they like best. I can recommend this book to all algebra students and to their teachers as well." Joselito Bautista, corporate planner and math enthusiast, top-notcher of the of the Electrical Engineering Board exam of 1980 wrote, "This book unlocks the ideas behind algebra as applied to arithmetic. To teachers, students, and enthusiasts of mathematics, go forth and multiply, using the techniques in algebra made easy as arithmetic." P.J. Zuluaga-Makiling, a certified Mathenic instructor, is a math teacher and early childhood educator in Bacolod City. She wrote, "As a BS Applied Math graduate and a math teacher, I was pleasantly surprised at how many of the concepts in algebra had concrete counterparts in arithmetic. The book points out things that make algebra easy. Learning the techniques would make learners change their view and attitude towards this math subject. I'd recommend this book to both math teachers and students alike." Former Dean at the College of Engineering, Architecture, and Technology, Palawan State University, Isaac Pitcairn Menzoyap, a certified math instructor, wrote, "With this book, students can have a better grasp of algebra. The approach is very different from the algebra we used to know. Students can discover that algebra is something to enjoy, not something to be afraid of." Today, it is with pleasure that we share with you Mr. Ike Prudentius' Algebra Made Easy as Arithmetic. Algebra Made Easy as Arithmetic is an initial attempt to demonstrate how application of some basic arithmetic procedures can greatly simplify many algebraic operations. The book contains some simple arithmetic techniques not commonly taught in schools today, but have valuable applications in algebra. Students familiar with these arithmetic techniques will find most of their future algebraic lessons very easy to understand and learn. We will discuss some Vedic mathematics techniques in arithmetic which must be taught during the early grades so that teaching and learning algebra in the higher grades will be easier. Our first lesson in Chapter 1 is the digit sum. The digit sum, also called repeated digital sum or digital root of a number, is a value found by adding the digits and the number. If the result is a number with more than one digit, we add again until a single digit is reached. Examples. What is the digit sum of 34? To find the digit sum of 34, we add 3 and 4 to get 7. The digit sum of 34 is 7. Another example. The digit sum of 48. Again, to get the digit sum of 48, we add 4 and 8. 4 plus 8 is 12. But since 12 is a two-digit number, we add the digits up again. 1 plus 2 is 3. So, the digit sum of 48 is 3. How about the digit sum of 21,368? So we add the digits, 2 plus 1 plus 3 plus 6 plus 8 to get 20. 20 is a two-digit number, so we add the digits up again. 2 plus 0 is 2. So the digit sum of 21,368 is 2. Casting out nines. Let us study the 9-point circle, in which the numbers from 1 to 9 are drawn around a circle, as shown here. If we continue numbering around the circle, we would place 10 after the 9, which is in the same place as 1, and then 11 at the same place as 2, and so on. We can see that numbers in the same place have the same digit sum. Since 0 is before 1, it occupies the same place as 9. telling us that 9 has the same effect as 0. Therefore, adding 9 to any number will not affect its digit sum. When we are getting the digit sum of a number, we can cast out or cancel any 9s, any numbers adding up to 9 or to a multiple of 9, and still get the same digit sum. Examples. Let's take a look at some examples here. If, for example, we're looking for the digit sum of 59, we can cast out 9 and get 5. How about the digit sum of 345? We see that 4 and 5 add up to 9, so we can cast out 4 and 5 to get 3. The digit sum of 345 is 3. How about the digit sum of 53,731? We can cast out 5, 3, and 1 because 5, 3, and 1 add up to 9. And now we're left with 7 and 3. 7 plus 3 is 10, but since it's two-digit number, we add it up again. 1 plus 0 is 1. So the digit sum of 53,731 is 1. How about the digit sum of 47? We don't have a 9 or numbers that add up to 9. But we know that 4 is the same as 2 plus 2. And 2 plus 7 is 9. So we can cast out 2 and 7. Now we're left with 2. So the digit sum of 47 is 2. Now let's recall the divisibility rules for 9 and 3, wherein digit sums are used. A number is divisible by 9 or 3 if the sum of the digits is divisible by 9 or 3 or equal to 0. What is not often emphasized is that the digit sum is the remainder when the number is divided by 9. This can also be extended by casting out 3's to get the remainder when the number is divided by 3. Now let's take a look at some examples. Is 246 divisible by 3? So we can add 2 plus 4 plus 6, which is 12, and 12 is divisible by 3. So 246 is divisible by 3. Now let's have a different example. What digit or digits can replace the x so that the number 9x3, 4, 5, 6 will be exactly divisible by 9? We know that if the digit sum of that is 9, then it will be divisible by 9. So we can start by canceling or casting out the 9's and the numbers that add up to 9. So we can cast out 9, 3 and 6, which is also a 9, and 4 and 5, which is also a 9. So for the number to be divisible by 9, the x should either be 0 or 9. How about what is the remainder when 44,612 is divided by 9? We can cast out 9's and numbers that add up to 9 again. So we see that 6, 1, and 2 add up to 9, so we can cast that out. And now we're left with 4 and 4. 4 plus 4 is 8, so the remainder is 8. Digit sums may be used to check if your multiplication is correct. A Vedic Math Sutra states that the product of the digit sums is equal to the digit sum of the product. Passing this method will not guarantee a correct answer, but it will help you spot a wrong answer. Another word formula that we can use to check our basic operations is the first by the first and the last by the last. This has many applications, but we will use it primarily for checking multiplication and in factoring. The first by the first and the last by the last is very useful in spotting mistakes in multiplication. It's particularly handy in choosing the correct answer in multiple choice questions and may be used in combination with the digit sum check. So here we're going to use the first by the first and the last by the last, and the digit sum check, or the product of the sum is equal to the sum of the product, to simplify or to find our answer in a multiple choice type of question. So let's take this example. What is the product of 38 and 65? So we're given the choices: A, 2,465, B, 2,470, C, 2,475, and D, 2,480. So let's write 38 times 65 first. Using the last by the last, we see that 8 times 5 is 40. So we know that the product must end in 0. If the product must end in 0, we can quickly eliminate options A and C. A cannot be 2,465 or 2,475. Using the digit sum check, we know that we can write it like this. You have 3 plus 8 times 6 plus 5. 3 plus 8 is 11 times 6 plus 5 is 11. So 1 plus 1 is 2. 1 plus 1 is 2 again. So 2 times 2 is 4. We know from this that the product must have a digit sum of 4. The digit sum of 2,480 is 2 plus 4 plus 8, which is 14. 1 plus 4 is 5, so the digit sum is 5. So it can't be the answer. So we're left with 2,470. What is the digit sum of 2,470? We can cancel 2 and 7 to get 9, so we're left with 4. Okay, so the digit sum of 2,470 is 4. So 38 times 65, without solving, we can get 2,470. Let's take a look at another example. What is the product of 37 and 43? Our choices are A, 1,141, B, 1,429, C, 1,591, and D, 2,131. Let's write it like this: 37 times 43. Again, using the last by the last, we multiply the last digit. 7 times 3 is 21. So our ending digit should be 1. So we can eliminate B, 1,429. Now let's take a look at the initial digits, the first by the first. Our lower limit would be 3 times 4 is 12. And then if we add 1 to it, that will be our maximum limit. 3 plus 1 is 4. 4 plus 1 is 5. 4 times 5 is 20. So the initial digits should be between 12 and 20. So it can't be A. It can't be 1,141, and it can't be 2,131 because it's just too much. So our answer is C, 1,591. Chapter 8.1 of the book discusses how we can use the Vedic Maths Sutra vertically and crosswise to multiply 2-digit by 2-digit numbers without regrouping. It can be done mentally in 3 simple steps. The first step would be to multiply vertically the left-hand column. Then we multiply crosswise and add the partial products. And lastly, we multiply again vertically the last column. Example, 12 times 32. Let's write them first vertically for better visualization. Like this. First, we multiply vertically the left-hand column. 1 times 3 is equal to 3. Then, we multiply them crosswise before adding the results. 1 times 2 is 2. 2 times 3 is 6. Adding the 2, we have 2 plus 6 is 8. Then lastly, we multiply vertically the last column. 2 times 2 is 4. 12 times 32 is equal to 384. We can use the same technique that we use to multiply two-digit numbers to multiply binomials. To multiply binomials, first we multiply the left-hand column vertically, and then we multiply crosswise and add the partial products, and lastly we multiply vertically the last column. Let's take a look at some examples. If, for example, we have 3x plus 2 times 2x plus 5, first, we can write them vertically, like this. Then, we multiply vertically the left-hand column. 3x times 2x is equal to 6x squared. Next, we multiply crosswise and add the results. 3x times 5 is equal to 15x. 2 times 2x is equal to 4x. Adding the 2, we get 15x plus 4x is equal to 19x. Lastly, we multiply vertically the right-hand column. 2 times 5 is equal to 10. 3x plus 2 times 2x plus 5 is equal to 6x squared plus 19x plus 10. Chapter 21. The product of the sums is the sum of the products. We can check the accuracy of our answer in polynomial multiplication by using the sutra, the product of the sums is the sum of the product, or PSSB. If, for example, we have 3x plus 2 times 2x plus 5, and we found that the answer is 6x squared plus 19x plus 10, we can first use the coefficients of 3x plus 2, which is 3 and 2, and the coefficients of 2x plus 5, which is 2 and 5. So we find that 3 plus 2 is 5 and 2 plus 5 is 7. Multiplying them, we get 5 times 7 is equal to 35. Then next, we move to the next side, or to the right side. We find the sum of the coefficients of the product. We add 6 plus 19 plus 10, which is also 35. Since both sides are 35, then most likely our product or our multiplication is correct. We can also use the vertical and crosswise method to multiply longer numbers of equal length. If, for example, we want to multiply a 3-digit number by another 3-digit number, we can first multiply the left-hand column, and then we can multiply the first two columns crosswise and then add the partial products. Then next, we multiply crosswise all the 3 columns and add the partial products. Then we multiply the last 2 columns crosswise and add the partial products. And then lastly, we multiply the last column, or the right-hand column. Let's take a look at an example. 514 times 632. We can write it first vertically for easier visualization. First, we multiply vertically the left-hand column. 5 times 6 is equal to 30. Next, we multiply the first two columns crosswise and get the sum. 5 times 3 is 15. 1 times 6 is 6. Adding the 2, 15 plus 6 is 21. Combining 30 and 21, we get 321. Next, we multiply crosswise all the three columns. 5 times 2 is 10, 1 times 3 is 3, and 4 times 6 is 24. Adding the three partial products, we get 10 plus 3 plus 24 is equal to 37. Regrouping the 3 of 37 to 1 of 321, we get 3247. Next, we cross multiply the last two columns. 1 times 2 is 2. 4 times 3 is 12. Adding the 2, we get 2 plus 12 is 14. Combining the 14 to 3247, we get 32484. Lastly, we multiply vertically the last column or the last digits. 4 times 2 is 8. Combining 8 to 32484, we get 324848. 514 times 632 is therefore equal to 324,848. We can extend the use of the vertically and crosswise method to multiply trinomials and longer polynomials of equal length. If, for example, we want to multiply a trinomial by another trinomial, we can first multiply the left-hand column and then multiply the first two columns crosswise and add the partial products, and then multiply all the three columns crosswise and add the partial products. Then multiply the last two columns crosswise and add the partial products. And then lastly, we can multiply vertically the right-hand column or the last column. In fact, algebraic multiplication is even easier than multiplying long numbers of equal length, because algebraic multiplication does not involve regrouping. Let's take a look at an example. X squared plus 2x minus 1 times 2x squared minus x plus 3. First, we multiply vertically the left-hand column. X squared times 2x squared is equal to 2x to the fourth. Next, we multiply the first two columns crosswise and get the sum. X squared times negative x is equal to negative x cubed. 2x times 2x squared is equal to 4x cubed. Adding the 2, we get negative x cubed plus 4x cubed is equal to 3x cubed. Then, we multiply crosswise all the three columns. We get x squared times 3 is equal to 3x squared. 2x times negative x is equal to negative 2x squared. Negative 1 times 2x squared is equal to negative 2x squared. Adding the three partial products, we get 3x squared minus 2x squared minus 2x squared is equal to negative x squared. Next, we cross multiply the last two columns. 2x times 3 is equal to 6x. Negative 1 times negative x is equal to x. Adding the 2, we get 6x plus x is equal to 7x. Then lastly, we multiply vertically the last terms, or the right-hand column. Negative 1 times 3 is equal to negative 3. Therefore, x x squared plus 2x minus 1 times 2x squared minus x plus 3 is equal to 2x to the fourth plus 3x cubed minus x squared plus 7x minus 3.